Beginning in the first chapter, we talked about using samples versus population. So finally in this chapter, we're going to talk about how to actually do some samplings, how to choose the individuals, two different sampling methods. We'll talk about errors that occur when you sample. We'll talk about sampling distribution of the sample mean, the Central Limit Theorem, and how to compute a z-score based on a sample mean as opposed to a population value. Now, the whole gist of this chapter really is going to be to prove that you can use samples to represent populations. Let's just do a quick review of what we're talking about when we're talking about a sample. Remember that a population includes every person, object, or item within the group that you're studying. A sample is a representative portion or a subset. Why do we work with samples? Because surveying the entire population could be quite expensive and time consuming, and sometimes if you're, for instance, doing a taste test, surveying or testing could be destructive. So in this chapter we'll talk about how to select a sample so that we can ensure that it is an accurate representation of the population. Right, in our discussion of sampling methods, the first method we'll talk about is simple random sampling. And whenever possible, this is the absolute best way to choose individuals that will be representative of the population. And in simple random sampling, any one individual has an equal chance of being selected. So no item or person or group or whatever you're studying is selected beforehand or targeted. And so examples might be just drawing a name out of a hat, using random number generator. You could actually use Excel to generate random numbers, but simple random sampling is the best way to ensure that you have a representation of the population. Another method that is commonly used is systematic random sampling. Let's say that you have a list of all of your employees and you're wanting to sample a group of your employees. You might list them by employee number and then just decide to choose every fifth employee, every sixth employee, systematically choosing individuals at random. We've mentioned that we can use samples to represent populations accurately. However, there are times when we're going to get some errors, and so we call that sampling error. And so, for instance, if we survey a population and we end up with a particular mean, and then we pick a couple people at random, or two or three or four or five, and we sample those and compute a mean. If there is a difference, and there most likely will be, we call that the sampling error. So the sampling error is the difference between the statistic and the parameter. Remember, statistics are what you compute from samples. Parameters are what you compute from populations. So the difference between the sample mean and the population mean, the sample variance and the population variance, and the sample standard deviation and the population standard deviation are called sampling error. As we begin our discussion of the sampling distribution of the sample mean, let me just remind you that the whole purpose of this is to illustrate mathematically that samples can represent populations. So, a sampling distribution of the sample mean is much like a probability distribution. It's going to list each and every possible outcome and the result. So with a sampling distribution, we have all possible sample means you can generate from a particular size of a sample, which we designate with a lowercase n. So let's assume, as this table shows, that we have a statistics class with 10 students in it. And we've decided to select 2 students at random and see if those 2 students that we've selected, if their mean is close to the population mean. So in this case, notice that we have a mean of 3.11. Just kind of keep that in the back of your head and we'll see if a 2 individual sample can represent that accurately. Well, because the sampling distribution of the sample mean is going to represent all possible samples that we can take, we need to determine how many different samples that we can get with 2 individuals. So this is one of those situations in which we'll use the combination formula. So with the combination formula, and here I have the Excel function shown on the screen here, we have an n of 10, a capital N of 10, which is the population size. We have a lowercase n, which is the sample size of 2. And so using the combination formula, either computing it longhand or using Excel, we end up with 45 different possible combinations of 2 students. Well, let's go ahead and see how that works when we actually create a sampling distribution of the sample mean. All right, remember that a sampling distribution is every possible sample that you can get from the population size and the sample size. And so you see an example of that on the screen here. So look at the first 9 rows. We have Ahmad and Alicia, Ahmad and Bob, Ahmad and Charles, Kathy, Maria, Min, Thomas, William, and Xavier. So a mod can have 9 different combinations, and that will vary as we go down the list here, and we end up with 45 different combinations. Well, let's just focus on line 1. So we have Ahmad and Alicia. We've computed the mean of those two, a sample size of 2. We end up with a sample mean of 3.05. Now that is not the same as the 3.11 population mean that we computed a minute ago. So we have an error. That's called the sampling error. Notice that the far right column gives us the error. Well, here's the interesting thing. Now, I have deleted a few rows here just to get it to fit on the screen. So from 18, I jumped to 35 here. But if we were to do all 45, and you could do that in Excel or go to my website and actually find this, you'll see that the mean of the sample means is exactly the same as the population mean. Also, if we sum up all of the sampling errors, we get an error of 0. Now, this is a super important concept. That means if you sample everybody, even just doing 2 at a time, you will end up with the population mean. So the concept here is that samples can accurately represent the mean. Now, we'll get into this in just a second here, but the larger the sample size, the more accurate it's going to be right off the bat. And that'll make more sense as we continue on here. We've also spent a lot of time up to this point talking about the normal curve. Now, the central limit theorem tells us that the sampling distribution of the sample means will approximate a normal curve, a normal distribution. And the larger the sample size, the closer to a normal distribution that actually becomes. Now, as an illustration here, just take a look at the curve that you see on the screen generated from the bars here. So these are the population GPA scores, and I've grouped them with a width of 0.2. Frequency distribution, and then we have a curve here. Notice that that's not a normal curve, that's an inverted curve. So the population in this case is not representative of a normal curve. However, as we're going to see in the next slide, the sampling distribution of the sample means is going to be because of the central limit theorem. All right, here we see a frequency distribution of the sample means, again with the width of 0.2. And we can see that even with a sample size of 2, and again there are 45 different combinations here, that we begin to approximate a normal curve. The larger the sample size, the more accurately that's going to be represented by a normal curve. So what's the big deal here? Well, the big deal is the central limit theorem allows us to represent our data with a normal distribution curve. That means that we can actually compute z-scores to figure out the area under the curve. Now, as you progress through statistics, you're often going to see the words, assume the data is normally distributed. Well, that's because we can really assume that, because based on the central limit theorem, the sampling distribution of the sample means tells us that the sampling distribution of the sample means can be represented by a normal curve, and as we've also learned, sample means can represent population means. As I just mentioned, because of the central limit theorem, we can use sample means and we can find areas under the curve using z-scores. However, we will use a slightly different formula to compute a z-score based on a sample mean. And so here we have the formula on the screen here. We have the x bar minus mu. So in this case, we have to know the population mean, and that becomes one limitation of using z-scores with samples, but we will cover how to get around that in additional chapters here. But also notice that the n, the lowercase n, which represents a sample size, is a significant factor in this equation. So the larger the sample size, the more accurate our statistics are going to become. All right, let's run through an example of computing a z-score based on a sample mean. Now, in the 10-student class, we already computed a population mean of 3.11. Remember, that is key in order to use z-scores for a sample mean. We didn't compute it on screen, but the standard deviation is 0.5643. So what we want to find out here, since we know the population mean, is we're going to select 2 students at random, and we're going to see if the mean of those 2 students accurately represents the population. So in this case, we use Alicia and Bob. We selected them at random. We have 2.3 for Alicia and 2.5 GPA for Bob. The sample mean of these 2 students is 2.4. So are these 2 students do they accurately represent the class as a whole? Well, we'll find out using z-scores. All right, bear with me as we run through this here. It's going to seem a little bit complex, but it's really not. So we have the mean of those two students of 2.4, and that is less than the population mean. We already know it is not a representation, but how accurately does it really represent that GPA? So what we're going to ask using the z-score here is, what is the likelihood or the probability of finding a GPA of 2.4 or lower? So we're going to solve that using a z-score. So we have the sample mean, we have the population mean, we have the standard deviation, and we have the square root of n, the sample size, and we end up with a z-score of negative 1.78. So the z-score is negative, which is because it is less than the population mean. So in this case, we're working with the left half of the curve. So we want to find the area associated now with a z-score of 1.78. Using the normal distribution table, we find that that area is 4625. Now let's see how we interpret that in the next slide. All right, so how are we going to interpret that sample mean of 2.4? Well, again, the z-score that we computed is negative 1.78. We see on the screen how that relates in the normal curve. Getting a sample mean of 2.4 or less, there's really only a 3.75% chance of that. So going in the opposite direction, if I were to take a sample mean, what would be the likelihood or the probability of getting a sample mean higher than 2.4? Well, that would be almost a little over 96%, 96.25%. So either way, that's telling us that a sample mean of 2.4 does not really, it's not really the best representation of the typical student of the course. Well, that's just representing a sampling error. That tells us why we might want to take more than one sample. It also hopefully lets us see why a larger sample size might reduce that sampling error. Again, even though the two students that we use as an example did not accurately represent the typical student, if we did survey enough students, sample enough students, we would arrive at a GPA very close to the population GPA. And remember, because of the central limit theorem and knowing that the mean of the sampling distribution equates to the population mean, it means that we can indeed use samples to accurately estimate population values, or as we call them, parameters. All right, let's just do a quick review of what we covered in this chapter. We talked about sampling methods. We talked about simple random sampling, where no one item has any more chance of being selected in the sample than any other. We talked about systematic random sampling, where we're going to take, for instance, the every fifth individual or the ninth individual from a list. We talked about sampling error, which is the difference between the sample statistics and the population parameter. Then with the sampling distribution of the sampling mean, a listing of all possible outcomes and the means, we learned that it is possible for sample means to estimate accurately the population mean. In fact, we saw that the sampling error equates to 0 when we sum it up, and that the mean of a sampling distribution of the sample mean is exactly equal to the population mean. We learned that the central limit theorem allows us to represent our data with a normal distribution because of the sampling distribution equates to a normal distribution. The larger the sample size, the more closely it is distributed with the normal curve. We also learned how to compute a z-score from a sample mean. We have to know the population mean, and that becomes one of the drawbacks in using sample z-scores, and we'll learn how to get around that in the upcoming chapters. And remember, all of these lessons are based on my textbook, Surviving Statistics, which is available on Amazon. And do remember to check out my website for downloadable files, calculators, and other resources.